Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 44 on the subject of computer organization and assembly language programming. The title of today's session is C function calling convention and the function stack frame. Well, this slide shows the agenda of today's session. First of all, we will have a quick recap of previous two sessions in which we covered the concept of writing our own assembly procedures, passing arguments and returning values from them. And today we will understand how high-level languages like C and C++ do the function calling. We will understand the concept of function stack frames, also called activation records, which is a stack data structure used to store all the data on the stack associated with a high-level language function. We will also see a demonstration showing and describing the code generated by a C compiler for the maintenance of this FSF on the runtime stack. And finally, I will close today's session with a practical demonstration of a stack-based buffer overflow vulnerability and a concept of exploiting it. Okay, so first, quick recap. We have seen this code in lecture 42 to understand the shifting of flow control from the caller to the callee and then back. Well, this call instruction first saves the return address, that is the address of the next instruction in sequence, by pushing the contents of RIP register on the stack over here. And this is how it is done. This call instruction then performs an unconditional jump to the first instruction following the label print message, and the code inside this function executes. And finally, this ret instruction pops the saved return address from the stack and place it inside the RIP register, thus shifting the control back to the caller. Well, dear students, in lecture 43, that is the last session, we discussed the calling convention used by different operating systems on x86-64 machines. And this slide summarizes the System 5 AMD 64 application binary interface that use 6 registers to pass integer arguments, and in case of more arguments, push them on the stack, and to return an integer value from a function, this RAX register is used. Okay, now let us switch gear and see how high-level languages make the function calls and how the runtime stack is used by the code generated by a C compiler. Okay, dear students, consider this C program having two functions, main and foo, where main is the caller and the foo is the callee. Well, over here the values passed by the caller to the callee are called arguments. So the foo function is passed 2 arguments, and once these arguments are received by the callee, they are called parameters. And this is the logical address space of this process. Note the process stack at the top having 2 portions of memory allocated for each function. Well, dear students, these 2 portions of memory on the stack are called function stack frames or activation records, which is the main topic of today's discussion. Every function has an FSF associated with it, in which that function stores all the data that is required for its execution. Okay, so far so good. Uh, let's now consider this sample C program having four functions. The main function calling a function f1, which is further calling f2, which is further calling f3. Uh, the f3 function return to f2, which returns to f1, and f1 returns to main, and which finally, of course, returns to its caller, that is the underscore start function of the C runtime environment. When the control of execution is at the first instruction of main, the runtime stack contains the function stack frame of main only. And once the control of execution is inside the function f1, the runtime stack contains another function stack frame for the function f1. And when the control of execution is in f2, the stack contains the FSF or activation record of f2. And finally over here we have four activation records on the stack, one for each function. Once this f3 returns to f2, note the function stack frame of f3 has been removed from the stack, and once f2 returns to f1, the function stack frame of f2 is removed, and finally when f1 returns, the function stack frame of f1 is removed. And now since the execution is inside the main function, only the FSF of main function is there. And finally this main function returned to its caller. So using this illustration, I have tried to explain as to how function stack frame of a function is created on this runtime stack. And when a function is called, we say that the stack is growing. And of course, stack grows from higher addresses towards lower addresses. And similarly, we have seen as how the stack shrinks when a callee returns to its caller. Okay. So well, dear students, this slide shows the contents of a single function stack frame on x86-64 machine running a Unix-based operating system. So this is a function stack frame containing four major items. Well, the initial 6 arguments are passed via registers, and if more than 6, the function arguments are pushed on the stack. Then we have the return address of the caller. Then the current contents of the base pointer or RBP register is also saved or pushed on the stack. And finally, we have space for the function local variables. And this is the overall function stack frame of any function that is called from main. Okay. Dear students, let us take a deep breath and do a scuba diving with me to understand as to how on an x86-64 machine running Linux operating system, the function stack frame for a function is created. First of all, the caller moves the first 6 arguments inside registers, and in case of more arguments, the remaining are pushed on the stack from right to left. Well, then the contents of RIP register, that is the return address of the caller, is also pushed on the stack. Well, this is a typo. And after the control is shifted to the first instruction of the callee, it performs a procedure prolog. And the first instruction of procedure prolog that we will soon see on the terminal as well is push RBP. So the RBP, which is pointing over here before the function was called, is pushed on the stack. And after that, we execute this instruction, move RBP, RSP, thus moving the contents of RSP inside the RBP register. So RSP and RBP after this instruction both will point to this location, and this is shown over here. RSP and RBP both are pointing to the start of the function stack frame of this function now. And finally, we perform a subtract instruction. We subtract some hex value from RSP. Thus, this RSP will be moved down over here. And now this is the function stack frame of the function that is called, containing the four components: function arguments, return address, base pointer, and space for local variables, with the base pointer pointing to the start of the function stack frame and RSP at the top of the stack. Well, dear students, when the Kali is done with its execution, it first cleans up the FSF and then calls the return statement to transfer the control to its caller. And this piece of code is called a procedure epilog. So the first instruction that we will come across is the leave instruction, which will do a reverse of this. That is, this instruction was move RBP RSP. This instruction is move RSP RBP. That is, the contents of RBP will be placed inside RSP. This can be observed over here. So both RBP and RSP are not now pointing to the start of this function stack frame. And another associated instruction with the leave instruction is pop RBP. Not we have push RBP over here and we have pop RBP over here. So this RBP will be removed from the stack and placed inside the RBP register, which will move back over here. And this is shown like this. So now the function stack frame of the main function is being pointed by the base pointer as well as the RSP. Finally, the next instruction you will come across is the ret instruction inside a procedure prolog, which will perform an unconditional jump by doing a pop rip instruction. That is, this address will be popped off from here and placed inside the RIP, and the control will move back to somewhere inside the main function. And this is how this entire function stack frame of the Kali is removed from the stack. Okay, my dear students, when you happen to see the disassembly of a C function, it will always start with a procedure prolog having these three instructions that actually creates the activation record of a function. And the disassembly of every C function will end with a procedure epilog, that is this leave and ret instruction. And these two instructions actually removes the activation record of a function from the runtime stack. And here is a concrete example, a C example. Note that the main function over here in this piece of code is passing 8 arguments to a function named foo over here. From right to left, this hex 48 value is pushed on the stack. This is shown over here. And then this hex 47 value is also pushed on the stack over here. That is, the function arguments are pushed on the stack from right to left. After these two additional arguments, more than 6 arguments, this is the 6th argument, which will be placed, of course, inside the R9 register. This hex 45 will be placed inside the R8 register, and so on. And this first argument, that is hex 41, this will be placed inside the RDI register. And after these registers are placed over here, the return address, of course, will be pushed, and the base pointer will be placed over here. Some space for the local variables of foo will be created, and the control will be transferred over here, and it will run. Dear students, I think enough of theoretical discussion has been made in this regard, and now is the time to move on to a Linux terminal and see a demonstration of all these concepts by loading this C program function underscore calling.c inside the GDB with the PDA plugin. And let me show you the code first. Cat function calling.c. Okay. So dear students, over here, you see the main function is calling function 1 and is passing 8 arguments to it. Over here, the function 1 is further calling function 2, which is a leave function, as it is not calling any other function. This function 2 returns the control to function 1, as it is a void function, so it is not returning any value, just returning the control. And this function 1 is returning a value of 54 decimal, as well as the control to the main function. This 54 will be received inside this integer variable rv, and the main function of course is returning the same value, that is 54, to the underscore start function of the C runtime environment, which we normally access inside the dollar question mark shell environment variable. Let me compile this program with the debugging symbols, function calling.c. Let me execute it and let me show you the return value, and that is 54. So that is great. Let me clear screen and let me now load this program inside GDB in quiet mode. A.out. Oops, GDB. Sorry for the typo. So great. So the PIDA plugin is enabled. So we have the GDB PIDA prompt, and let me shrink it a bit and show you the disassembly of the main function first. Okay. Well, dear students, this is the disassembly of the main function. Note these first 3 instructions of procedure prolog in the beginning that actually creates a function stack frame for this main function. And do note these last 2 instructions, the leave and ret, which are the procedure epilog used to roll back the FSF of this main function from the runtime stack. And let us understand the remaining part of this code in this disassembly generated by GDB by showing you the C code by listing it. I think it is from 20 to 23. Well, this is the main function. Note this 8th argument, that is hex 48, and this 7th argument hex 47. They are pushed on the stack. So they are pushed on the stack from right to left. First hex 48 is pushed, then this hex 47 is pushed. Then the remaining 6 arguments are moved inside registers. Note this 46 is moved inside R9 register, since this is it is considering it a 32-bit value, so it is using R9D. Anyway, so these are the 6 registers, EDI or RDI, RSI, RDX, RCX, R8 and R9. So all the 8 arguments which the main function want to send to this function before calling it are pushed on the stack and placed inside the register. Okay, so this function 1 is called over here. Let's see the disassembly of function 1 as well. We disassemble function 1, and let me show you the code at the same time. List 16 to 19. Okay, so once again over here you see the procedure prolog, and at the end of this function we have the procedure epilog. And also note that before returning to the main function, it is moving hex 36 value inside the EAX register or RAX register, so that this value can be returned to the main. Do note that the 6 register parameters RDI, RSI, RDX, RCX, R8 and R9, they are moved from the register onto the stack. Well, all the stack memory references are made with respect to the RBP register as shown over here. So this RDI is moved to an address inside the stack relative to RBP and this RSI and this RDX as well. I hope this makes sense. And after all this, this function, that is function 1, is going to call function 2. And let us see the disassembly of function 2 as well. P disassemble function 2, and let's see the high level code as well. That is from line number 12 to 15, I think. Well, yes, it is true. Well, dear students, note that since this function 2 is a leaf function, by leaf function I mean it is not calling any other function, therefore you do not see the subtract instruction over here inside the procedure prolog, and of course you do not see the leave instruction inside the procedure epilog. Well, dear students, actually the compilers use the 128 bytes red zone beyond the RSP register for all the temporary data required by our leave function. So leave function do not need to subtract a value from the RSP to move to a higher or lower location to accommodate the local variables. Local variables are created inside the red zone. Okay. One last thing is that in the high level language over here, since the function 2 is just returning control and not any value, therefore over here in the assembly, or rather disassembly of the compiler, you can note that the compiler is not moving any return value inside the EAX register before calling the ret statement. Great. Okay, so now we have seen the C and the corresponding disassembly of all the 3 functions that are there inside the program. Let us run it. Let me put a break at main. Program is already loaded. Great. Let me do a run. So it is running right now. Let me shrink the code a bit. These are the registers, contents of the registers shown, the flags as well. Over here we have a portion of the code, and right now you can observe that we are inside the main function, and over here we have the stack. So if I think you are quite comfortable with GDB with PIDA plugin, the interface which we have covered in the previous many sessions. Let me press SI to execute this instruction. So this instruction is going to push the 8th argument on the stack. Keep a note of the stack. So it is pushed on the stack. This will push the 7th argument. Great. This will move the 6th argument inside R9 register. Keep a note of R9. So R9 contains this. And similarly, all the remaining values are also pushed on different registers. Keep a note of that. And finally, we are on the call instruction. Once we are on the call instruction, the 2 values, the 2 arguments, 7th and 8th, are on the stack. And of course, the RDI, RSI, RDX, these register contains the arguments A, B, C, D, E, F. These are the corresponding alphabets, ASCII alphabets of these ASCII codes. Great. And now is the time to make this call instruction. And before we make this call instruction, keep a note of the next address, that is 5518E. This will be pushed on the stack before the control is shifted to this address, that is 512C. Let me press SI. Keep a note, this address will be pushed on the stack and the control will move to this address. Great. This 5180 has been pushed on the stack and the control is there at 5512C, function 1, the first instruction of function 1, which will perform a procedure prolog. Let me keep pressing SI, and these are the instructions which are moving the contents of the 6 register on the stack. Keep a note of the register contents being moved on the stack. Okay, so all the contents are there on the stack: A, B, C, D, E, F, all the 6 registers, and the other 2 are already there. And now we are at the call instruction, which is going to call function 2. Now this address will be saved on the top of the stack, 5156, and the control will shift to 5125 address. So 5156 has been saved over here, and we have moved to the first instruction of this function 2, 5125, and over here, once this will be executed, having no instructions. Finally, this is the last instruction of function 2, which says ret. Now this will pop off this saved return address on the stack, and this address will of course move inside our IP register over here, and the control will be shifted there. Keep a note of that. So there you go. We are at 5156 instruction right now. The RIP register contains 5156. Now this function 1 will execute the last 3 instructions. The return value will be moved inside EAX. It will perform a leave and the ret instruction. Before we execute the ret, note that the return address is at the top, 518E, where we want to return, and EAX contains hex 36 value, which will be returned to the main function. So here we go. So we are at 5518E, which is the next instruction after the call of function 1. Let me move, keep moving ahead, keep moving ahead. And here we are at the ret instruction of the main function. And now the main will return to this address, which is at the top of the stack, 4E0B, which is the address of the underscore start routine inside the libc. So that is great. Let me press C to continue this program. So exit it normally. Let me press Q to quit, and let me fall back to slides. Okay, my dear students, I have tried that you should have a fair idea of how the function stack frames or activation records of functions are pushed on the stack or created on the stack, and how they are rolled back. I strongly recommend that you should download this program from the course Bitbucket repository and execute it inside the GDB with PIDA to have a crystal clear understanding of this concept. Okay, so before I close today's session, let me take this opportunity to discuss the stack-based buffer overflow vulnerability as well. And that is very much related with the function stack frames created on the runtime stack. Okay, dear students, consider this C program now, a very simple C program in which the main function is receiving command line arguments. It is then calling the function f1 by passing it arg v sub 1. That is the first argument, first string argument after the program name. This function f1 receives the address of the array inside a pointer variable named data. It then creates a local variable buff of 48 bytes and then use strcpy library function to copy the data received inside this local buffer. It then prints the contents of buffer on screen and then return the control to the main function. Okay, so this image over here, this shows the layout of function stack frame of the function f1. Keep a note of this function stack frame of function f1 over here. Note the function stack frame contains a space for any arguments more than 6 in case. Then we have saved the return address, the contents of RBP register, and then we have let's suppose 48 bytes space for this buffer, local variable created inside F1. Okay. Uh, Also note that when data is copied in the buffer array, the first 8 bytes will be copied over here, the next 8 bytes over here, next 8 bytes over here. I'm assuming that the width of this stack is 8 bytes, and moreover the writing in the buffer will move from the lower addresses towards the higher addresses. Okay, so this is how the data will be copied. The first 8 bytes have been copied over here. The next 8 bytes, the next 8 bytes. If only 48 bytes of data, that is 48 alphabet characters A's, are given by the user via command line argument to the main function, and the same is passed to this function F1, the things will work perfectly fine. My dear students, however, if the user has given more characters or alphabets than 48, then maybe this base pointer gets overwritten by these A's when this strcpy will copy this data to this buffer without taking care of any bounds. And maybe this address overwrites the return address as well, like this. And the return address gets corrupted. And if this happens, that is, this return address over here is overwritten by, let's suppose, alphabets A, then when this return instruction, return statement of C will execute, it will try to return to this corrupted address over here, A, which is of course not the address of the next instruction inside the main function. Rather, maybe this address is of a place that is not inside even the code section of this program. So you will get a segmentation fault. And we say that this C program suffers with a buffer overflow vulnerability. My dear students, if somehow you craft an input string for this program in such a way that over here at the place of the return address, instead of A's, we can write the address of a malicious function or malicious code, a shell code. That means you have successfully exploited this vulnerable program, because after that, once this F1 will return after executing this instruction, it will not return to this main function. Rather, it will return to some place where a malicious code resides, and that code will start executing and will perform whatever task you have written it for. Okay, dear students, please do download this C program from the course Bitbucket repository, bufferoverflow.c. Run it inside GDB with PETA to have a crystal clear understanding of what I have said in the last illustration. Do try to craft your input in such a way that the saved return address on the stack gets overwritten by the address of your malicious code. And if you are successful in doing that, that will be great. If not, I will plan to prepare a lab on this, and you will get it in your next coming Friday, inshallah. Okay, so that is all for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning, and Allah Hafiz.